Welcome to the Deep Dive, your express ticket to truly understanding the cutting edge of research. We live in an age where the pace of technological advancement is simply staggering.
It really is. Almost hard to keep up sometimes.
Every day, we demand more from our devices. Smarter, faster, and crucially, vastly more energy efficient.
That energy part is becoming a huge bottleneck, isn't it?
Totally. Think about the AI running directly on your smartphone, the lightning-fast signal processing in 5G networks, or the myriad sensors in your smart home constantly crunching data.
Yeah, these aren't just small upgrades anymore.
Exactly. They represent a fundamental shift in how we interact with technology. But there's a looming challenge, a fundamental bottleneck that threatens to slow this progress. How do we continue building these incredibly complex intelligent systems without hitting massive energy walls or getting bogged down in design processes that simply can't keep up?
Right. It feels like we're constantly pushing against the limits of what traditional digital methods can sustainably deliver.
Precisely.
It's a critical observation because at the heart of it, the physical world we inhabit, the one we're trying to model and interact with through these systems, is inherently analog.
Right. Continuous signals, not just ones and zeros.
Exactly. For many tasks, particularly those involving continuous data, direct analog computation can be profoundly more efficient than trying to digitize and then process that information.
But analog's always had this
Yes.
reputation, right?
It has. Historically, the Achilles heel of analog design has been its sheer complexity. Imagine if every component in a digital chip had to be custom designed and physically laid out by hand,
Oh, wow.
optimized pixel by pixel, without the aid of sophisticated software tools. That's been the reality for large-scale analog systems.
And that's precisely the crossroads we find ourselves at. Analog computing isn't just a nostalgic nod to the past. It's emerging as a powerful, necessary alternative to traditional digital approaches for specific high-demand tasks.
For certain jobs, it just makes more sense physics-wise.
But, as you rightly pointed out, analog has always faced this colossal hurdle. The glaring absence of robust automated design tools for complex systems.
Yeah, the digital divide in tooling is stark.
It's a stark contrast to the highly mature, almost hands-off automation that digital circuit designers have enjoyed for decades. That gap isn't just a nuisance, it's been a profound limitation, preventing analog from truly scaling.
It really has. What's truly fascinating here is that if analog computation offers such compelling advantages, energy efficiency, direct processing, why isn't it already ubiquitous?
Good question.
The direct answer lies in that digital divide we just mentioned. While we've seen incredible innovation in fundamental analog circuits, things like amplifiers or filters,
The building blocks.
exactly, the building blocks,
Right.
but scaling these handcrafted designs to build something as complex as a neural network or a sophisticated signal processor has been an incredibly specialized, time-consuming,
And therefore expensive.
prohibitively expensive endeavor, often. It often required years of experience from a handful of experts, essentially bottlenecking progress.
Well, today, we're tearing down that bottleneck. We're diving deep into a truly innovative solution that promises to bridge this very gap.
Okay, I'm intrigued.
We're talking about KALAM, which is a clever acronym for Toolkit for Automating High-Level Synthesis of Analog Computing Systems.
KALAM, got it.
KALAM's audacious mission is to bring the kind of seamless, digital-like automation that designers have craved, specifically to analog design,
Which is the holy grail, really.
particularly for systems built on a remarkably robust and versatile framework known as margin propagation, or MP.
Ah, margin propagation. Okay, I've heard good things about MP.
Exactly. So by the end of this deep dive, you, our listener, are going to grasp exactly how KALAM is not just optimizing, but fundamentally revolutionizing analog circuit design.
Sounds like a big claim. Let's see.
You'll understand how it's making complex, energy-efficient systems more accessible, faster to develop, and opening doors to a new era of computing.
So making analog design less of a black art.
Pretty much. This is your shortcut to being genuinely well-informed on a truly cutting-edge, game-changing field. So let's jump right in.
Let's do it.
Okay, let's unpack this. The core motivation for this whole resurgence in analog computing comes from a relentless, almost insatiable demand for computing systems that are not just powerful, but also exquisitely energy efficient.
The power issue is just paramount now, isn't it?
Absolutely, you see it everywhere.
Yeah.
From the need for intelligent interfaces that process sensory data with minimal lag and power, to advanced data compression algorithms that need to run continuously without draining batteries.
Like in wearables or edge devices.
Exactly. Our sources succinctly capture this as growing needs for intelligent, energy-efficient systems, and rising energy and performance demands. Now, for so long, digital has been king. Why is analog suddenly presenting itself as the answer to this energy and performance crunch? What inherent limitations have digital systems begun to hit?
Well, the why behind analog's resurgence is rooted in fundamental physics and the limitations of digital scaling. Digital computation, by its very nature, relies on discrete on-off states, represented by voltage levels.
Yeah.
Every time a transistor switches or a bit of data moves across a wire,
Energy gets used.
right, there's a capacitance that needs to be charged or discharged, which consumes energy. CV squared F, right? As we shrink transistors, leakage currents become a significant problem.
So even when they're off, they're leaking power.
Exactly. Burning power even when the chip isn't actively computing. Furthermore, digital systems often rely on a global clock, requiring precise synchronization.
Which itself takes energy.
Itself is a major power sink, especially at higher frequencies.
So it's not just about turning a transistor on or off, it's about all the associated overhead, the charging, discharging the leakage, the clocking.
Precisely. And for certain tasks, particularly those dealing with continuous real-world signals like audio, video, or sensor data.
The analog world.
Right. Digital processing involves a conversion step from analog to digital, ADC, and often back again, DAC. These converters are themselves power-hungry bottlenecks.
Ah, I see. Another energy cost.
And then you have the von Neumann bottleneck. In traditional digital architectures, data constantly shuttles between the processor and memory,
Back and forth, back and forth.
which is a major energy cost for data-intensive tasks like AI. Analog, in contrast, can often perform computation in situ directly on the signal itself,
Computing where the data is.
minimizing these energy-intensive data movements and conversions. It's a more direct pathway, leading to a clear need for advancements in analog hardware that can meet these energy and performance demands in ways digital simply struggles to.
That paints a really clear picture of digital's inherent energy wall for certain tasks, making analog's promise of native, continuous processing and energy efficiency incredibly attractive. And our sources highlight a particular standout paradigm that's leading the charge here: margin propagation, or MP.
Yes, MP.
This sounds like the secret sauce for making analog scale. What exactly is the margin propagation framework at a high level, and what makes it so uniquely promising?
Margin propagation, or MP, is truly a game changer in analog computing. At its core, it's a versatile analog computing framework that enables the robust and modular implementation of virtually any nonlinear monotonic function.
Any function. That's bold. How?
Think about complex mathematical operations, like a sigmoid curve used in a neural network or a logarithm, that are notoriously difficult to implement efficiently in traditional analog.
Right, those tricky nonlinear ones.
MP breaks these down by using piecewise linear splines. Imagine taking a complex curve and approximating it with a series of connected straight-line segments.
Okay, like drawing with short straight lines instead of one smooth curve.
Exactly. Each segment is simple, but together they can accurately represent a highly nonlinear function. This modularity, this ability to break down complexity into simple, repeatable blocks, is a critical feature that KALAM, our automation tool, leverages heavily.
So it's modular, which sounds like it could drastically simplify design by allowing complex functions to be built from smaller, manageable pieces, like Legos for analog functions.
That's a great analogy. But what are the other key advantages of MP that elevate it beyond just another analog technique? What makes it robust enough for real-world adoption?
Yeah, what makes it work reliably?
One of the most significant advantages, and arguably the most revolutionary for analog, is its scalability and inherent robustness.
Robustness. That's the key word I keep hearing about analog's problem.
It is. MP designs demonstrate consistent performance across a wide range of biasing conditions, temperatures, and diminishing process technology nodes.
Wait, so changes in temperature or manufacturing variations don't throw it off as much?
Much, much less. For decades, analog's Achilles heel was its unpredictability at scale. Tiny variations in manufacturing, temperature fluctuations, or voltage changes could throw a precisely tuned analog circuit completely off.
Making it a nightmare to design and guarantee performance.
A total nightmare. MP, however, with its clever internal architecture, essentially solves that predictability problem. It's not just an efficient circuit, it's an automatable one because it behaves reliably.
Ah, the reliability enables automation.
Precisely. This means an MP-based circuit isn't just a fragile lab curiosity. It can perform dependably in the messy, variable conditions of real-world applications, even as manufacturing processes shrink.
So it actually works outside the lab.
And we've seen its demonstrated success in energy-efficient, accuracy-tunable implementations, particularly in signal processing,
Yeah.
SP, and machine learning, MP processors.
Yeah.
This isn't just theory. It's been proven in silicon.
That's a profound insight. For a listener like me who's always heard analog described as inherently unreliable due to these very variations, MP's robustness is a huge selling point.
It's fundamental.
It's energy efficient, tunable for accuracy, and crucially robust across different conditions and manufacturing processes. And I also read that MP designs are considered pre-characterized and akin to a favorable analog standard cell.
Yes.
What does that mean for someone trying to design with them, and why is that so significant?
The term favorable analog standard cell is absolutely key to understanding MP's potential for automation. In digital design, engineers don't typically design individual transistors for every logic gate.
Right, they use libraries, AND gates, or gates.
Exactly. They use pre-designed, thoroughly tested, and characterized standard cells, like AND gates or gates, flip-flops from a library. You simply drop them into your design knowing exactly how they will perform.
Predictability.
Predictability and reusability. MP brings a similar level of predictability and reusability to analog. These MP building blocks, because of their inherent robustness, behave predictably. You can trust that these cells will work as expected,
Like digital standard cells.
making them much easier to reuse and integrate into larger systems. This is a monumental shift from traditional analog design, which often required highly customized, from-scratch optimization for almost every component.
So it moves away from that bespoke, artisanal approach.
It turns analog design from bespoke craftsmanship into something closer to building with advanced, reliable Lego bricks.
So we have this incredibly promising analog technology, margin propagation, that's energy efficient, scalable, modular, robust, and now, critically, it behaves like a digital standard cell.
Sounds pretty good, right?
It sounds almost too good to be true, like the ultimate solution. But you mentioned earlier that its widespread adoption for big projects has been limited. Why, after all these advantages, has it been held back?
Yeah, what's the catch?
What's the true bottleneck that KALAM aims to smash through?
Despite all of MP's inherent versatility in proving energy-efficient implementations, its adoption for large, complex systems has been severely hindered by the lack of digital-like automation tools for designing analog systems.
Back to the tools problem.
Always back to the tools. The core issue is that while MP offers amazing components, putting hundreds, thousands, or even millions of these analog standard cells together to form a complex system,
Connecting them all up, correct?
routing their interconnections, ensuring they all work together seamlessly, and validating the entire system, that process has still largely been manual and excruciatingly slow.
Like knitting a skyscraper.
Pretty much. Imagine trying to design a modern city layout by drawing every single pipe, wire, and road junction by hand. That's been the situation.
It's the classic scaling problem. Brilliant individual components, but no efficient way to assemble them into something grand.
Exactly.
But what you're saying also implies that MP's very modularity and scalability create a unique opportunity for automation. It's almost like MP is begging to be automated because its nature allows for it.
Precisely. You've hit the nail on the head. The very qualities that make MP so powerful, its modularity, its predictable behavior, its robustness, also make it uniquely amenable to automation.
Because the pieces are reliable.
You can build an automated design flow around it because its building blocks are reliable and well-defined. This is a much harder, almost impossible task for more traditional, highly custom-tuned analog approaches where every tiny change can have unpredictable ripple effects.
Right, the sensitive, temperamental stuff.
And that, fundamentally, is where KALAM steps in, to seize this unique opportunity and unlock MP's full transformative potential by providing that missing automation layer.
Okay, here's where it gets really fascinating for me. KALAM isn't just about making analog chips. It's about translating abstract, high-level concepts, things like probabilistic models, signal processing algorithms, or even neural networks.
The actual algorithms we want to run.
Directly into functional analog circuits. And it achieves this by leveraging something called factor graphs as its foundational paradigm for synthesizing MP-based analog computing systems.
Factor graphs.
What even is a factor graph, and why is this particular graphical representation so profoundly powerful for automated circuit synthesis?
To connect this to the bigger picture, factor graphs offer a truly universal, elegant language for modeling complex systems, especially those involving uncertainty, dependencies, or iterative computation.
Like probability or decoding signals.
Exactly. The genius is that by representing a problem in this highly structured, abstract graph format, KALAM gains the ability to systematically transform that abstract graph into a physical, energy-efficient analog circuit.
A direct translation from math to hardware.
Essentially, yes.
Mm-hmm.
It doesn't matter if you're trying to perform Bayesian inference, decode a noisy signal, or run an AI model, the factor graph provides a unified blueprint.
A universal language, that's a strong claim. Let's break it down for our listeners. What exactly constitutes a factor graph?
At its core, a factor graph is a bipartite graph.
Bipartite, meaning two parts.
Exactly. This means it consists of two distinct sets of nodes, and edges only connect nodes from one set to nodes from the other, never within the same set.
Okay, like boys only dance with girls, never with other boys, metaphorically speaking.
Sort of. Think of it like a bridge connecting two different islands, but no roads on the islands themselves connect different points on the same island.
Gotcha. Two distinct sets of nodes. What are they?
The first set are variable nodes, typically depicted as circles and denoted by V. These represent the underlying random variables in the system.
The things we don't know or want to figure out.
Precisely. For example, in a medical diagnosis system, a variable node might represent, does the patient have a fever? Or is the patient infected with X disease? In a communications system, it could be, was the transmitted bit a 0 or a 1? They represent the unknowns or the states we're trying to infer.
Okay, variable nodes and the other set.
The second set are factor nodes, usually depicted as squares and denoted by F. These are the crucial elements. They don't represent variables themselves, but rather functions or constraints that define the relationships or dependencies between the connected variable nodes.
So they represent the rules or the math connecting the variables.
Exactly. An edge connects a factor node to a variable node if that variable is an input to or influenced by the function represented by that factor node. For instance, a factor node might represent the probability of a fever given an infection, connecting the fever and infection variable nodes.
So if I understand correctly, a factor graph gives you this incredibly clear visual way to represent how different pieces of the variable nodes are intertwined and constrained by specific mathematical or logical relationships, the factor nodes.
You got it. It lays out the structure of the problem.
And this structured representation you mentioned enables powerful mathematical operations.
Absolutely. This graphical factorization is incredibly powerful because it allows us to represent a complex trait probability distribution of all the variables in the system as a product of these much simpler local functions defined by the factor nodes.
Breaking a big, scary problem into smaller, manageable pieces.
Exactly. This decomposition is what makes efficient inference algorithms possible. Instead of trying to solve one massive, intractable equation, you can break it down into smaller, interconnected local computations that iteratively share information, refining the overall solution.
Divide and conquer.
That's a divide and conquer strategy, perfectly suited for parallel processing and, as KALAM shows, for analog hardware.
That's a fundamental breakthrough for automating analog design. Factor graphs provide this elegant, unified language for describing many different types of problems. And KALAM then directly translates this abstraction into the physical reality of MP circuits. How versatile are these factor graphs in KALAM's context? What kinds of truly diverse, real-world applications can KALAM tackle using this approach?
The versatility is, frankly, astounding. Our sources state that factor graphs are the basis of various signal processing tasks, making them an incredibly powerful abstraction.
So not just one niche area.
Not at all. By coupling with MP, KALAM can design scalable and energy-efficient analog signal processors for an astonishingly wide range of applications. Let's look at some compelling practical examples demonstrating KALAM's reach.
Fantastic. Walk us through a few. This is where the rubber meets the road.
First up, we have Bayesian networks, BANs.
Okay, probability and inference stuff.
Exactly. These are directed acyclic graphs, DAGs, that are exceptionally good for modeling cause and effect relationships or conditional probability distributions.
Like figuring out the probability of something happening given other factors.
Precisely. Imagine a network that infers a medical diagnosis from symptoms or predicts customer behavior based on demographic data. In a BN, KALAM essentially treats each factor node, which encapsulates a specific conditional probability function, like PHC,
or the math rule,
as an MP analog soft gate. So you're translating an abstract probabilistic relationship directly into a physical, energy-efficient analog circuit component. This allows for real-time, low-power inference.
Wow. So KALAM can take a complex conditional probability, say the likelihood of a system failure given certain operational parameters, and map that abstract mathematical relationship directly to an analog circuit component using MP.
That's the idea, translating the probability table into hardware.
That's quite a feat. What about something that's foundational to modern communication, like error correction? Can it handle that?
Absolutely. Another crucial application area is message passing decoders, particularly for codes like low-density parity check, LDPC codes.
The LDPC codes, they're everywhere, right? Wi-Fi, 5G.
They're the bedrock of reliable digital communication, ensuring data integrity even over noisy channels. Here, KALAM leverages probabilistic message passing, and specifically the sum product algorithm, SPA.
Okay, SPA.
Which is an iterative decoding mechanism. The SPA is elegant because it allows for robust decoding by iteratively exchanging probability messages between variable and factor nodes.
Sending information back and forth on the graph.
Right, summing up likelihoods, multiplying them by constraints, a process surprisingly well-suited for analog computation, as it often involves current summation and voltage multiplication.
Ah, the physics aligns with the math.
These messages refine the probability of each bit being a 0 or a 1 until a reliable decision can be made. KALAM leverages existing MP-based LDPC decoder designs, showing it can effectively integrate and automate proven techniques.
That's incredible, translating something as abstract as message passing in a probabilistic decoder, where probabilities are iteratively refined, into an energy-efficient analog circuit. It really highlights how versatile factor graphs are.
It's a powerful abstraction.
And what about the elephant in the room these days? Artificial neural networks, ANNs. Can KALAM handle those complex parallel computations that power modern AI?
Yes, it absolutely can. For artificial neural networks, the mapping to factor graphs is quite intuitive and elegant. Neurons typically represent the variable nodes in the factor graph.
So each neuron is a variable we're calculating.
Pretty much. The factor nodes then correspond to activation functions, such as sigmoid or ReLU.
The nonlinear parts that give neural nets their power?
Exactly, which are applied to the weighted sum of inputs to a neuron, commonly known as the multiply-accumulate operation.
The META operation, the heart of neural network computation.
It's the workhorse, and MP circuits are particularly efficient at performing it. KALAM specifically uses MP, MCS, and MP activation functions that have been previously developed and optimized,
leveraging existing good designs.
Once again demonstrating its ability to integrate existing highly efficient MP components into a cohesive automated design.
So whether you're building a sophisticated probabilistic model for real-time inference, a robust communication decoder to ensure data integrity, or even an energy-efficient AI brain for edge devices,
A pretty wide range.
factor graphs provide this universal blueprint, and KALAM uses that blueprint to systematically construct optimized, energy-efficient analog hardware. That's not just a step forward, it's a fundamental leap in automated analog design, bridging the abstract world of algorithms with the physical reality of silicon.
It really aims to close that gap.
Having seen the urgent need for a new approach and how margin propagation offers us these remarkable, predictable building blocks, the natural next question becomes, how does KALAM actually assemble them?
Yeah, what's the actual process?
And this isn't just a collection of cool ideas, it's a functioning automated pipeline. Our sources describe a structured, automated flow, remarkably similar to how digital chips are designed, but tailored for analog.
Like a digital EDA flow, but for analog MP circuits.
Exactly. This is the KALAM blueprint, a meticulously engineered 5-stage process that takes abstract ideas and translates them into tangible, physically verifiable circuits. Can you give us the grand tour of this automated journey?
Absolutely. KALAM's 5-stage automation flow is a meticulously designed pipeline that systematically transforms a high-level problem description into a fully validated analog circuit netlist.
The final blueprint for the chip.
Automating what used to be a prohibitively laborious manual process. It's truly about bringing the efficiency of digital design automation to the analog realm.
All right, let's start at the very beginning, stage 1. This is where the user's intent first enters the system.
That's stage 1, factor graph generation defining the system. This is the initial input stage where the user defines the problem or system they want to build using the universal language of factor graphs.
Okay, feeding the blueprint in.
And KALAM offers flexibility here, accommodating 2 primary paths. First, for well-established designs like LDPC decoders, where the underlying mathematical structure is already known.
Like you have the parity check matrix.
Exactly. You can directly provide the factor graph given by the code's parity check matrix. This is essentially handing KALAM a pre-made, optimized blueprint.
Or
Second, if your system is described at a higher, more abstract level, for example, a Bayesian network represented as a DAG for probabilistic inference, KALAM can actually construct the appropriate factor graph for you.
oh, that's clever. It helps build the graph if you don't have one.
It handles the initial translation from a high-level model into its graphical representation.
So either you hand KALAM the factor graph, or it intelligently helps you build it from a higher level description. That streamlines the input significantly.
Definitely lowers the barrier to entry.
Once we have that precise graphical representation, what's the next step in this transformation?
That's the critical juncture where we move to stage 2, computational graph generation mapping operations. This stage translates the abstract relationships and dependencies within the factor graph into the actual mathematical and logical operations that need to be performed by the circuit.
Okay, turning the relationships into actual calculations.
It's where the what becomes the how to calculate. This involves several crucial substeps. First, a detailed analysis is performed to determine the number of inputs for each operation and the respective connections.
Figuring out the wiring, essentially.
Understanding the data flow. Then, and this is where significant efficiency gains are made, computational optimization eliminates redundant variables using variable elimination algorithms,
Getting rid of unnecessary calculations.
along with mathematical and Boolean simplifications, if any. This is absolutely essential to minimize the complexity and power consumption of the eventual circuit.
Smart optimization.
Finally, KALAM generates a visual representation of this computational graph using powerful visualization tools like the Graphis Python package for immediate visual verification.
So you can see what it's doing.
And validation against a software implementation to ensure mathematical correctness. This stage essentially defines the optimized algorithm the analog chip will execute.
That optimization step sounds absolutely crucial for both efficiency and accuracy. So we've gone from an abstract system description to a clearly defined optimized sequence of mathematical operations.
Right. A concrete plan for computation.
Now, how do we bridge the gap from these mathematical operations to actual analog circuits? This seems like the magic step.
It is pretty neat. That's the heart of the automation, stage 3. Analog circuit mapping. From graph to circuits. This is where the optimized computational graph truly becomes an analog map, assigning physical circuit components to each operation.
Okay, picking the right MP Lego bricks.
KALAM achieves this by optimizing computations with corresponding standard cells from a predefined analog standard cell library. These aren't just generic components, they are specialized MP-based cells.
The ones we talked about earlier.
That have been meticulously designed and characterized for specific trade-offs, enabling customization for varying accuracy, precision, power, and area budget.
So you can choose, do I need super accuracy or super low power?
Exactly. For instance, increasing the number of splines in an MP function allows for higher accuracy in approximating a nonlinear function. But this naturally comes at the cost of increased area on the chip.
The accuracy versus area trade-off.
Similarly, for power considerations, you can select cells designed to operate in a weak inversion regime for maximum power savings.
Good for battery-powered stuff.
Ideal for always-on-edge devices, or opt for a strong inversion regime for high-performance, higher-speed operations.
When speed is king.
The inherent modularity of MP circuits is a huge advantage here, making projecting the area overhead feasible and simplifying resource allocation. Before proceeding, this stage is also functionally validated using software tools to ensure the chosen analog components accurately reflect the mathematical operations.
So KALAM has this intelligent library of pre-designed flexible MP components that it selects and configures based on the specific operational needs and performance trade-offs, accuracy, power, area.
It's like having a highly specialized, optimized catalog of analog functions at its disposal.
It's like having a highly specialized, optimized Lego set of analog functions at its disposal. Once we have that detailed analog map, how does it become a tangible, manufacturable circuit design?
That brings us to stage 4, netlist generation, building the circuit. The analog circuit map from stage 3 serves as the blueprint for netlist generation.
The netlist. Define that for us again.
A netlist, for those perhaps less familiar, is essentially the precise text-based description that contains every single component, like transistors, resistors, capacitors, and crucially, all their interconnections.
The detailed wiring diagram for the factory.
Exactly. It's the detailed wiring diagram that is absolutely essential for circuit simulation and eventually manufacturing. KALAM fully automates this by instantiating the implemented standard cells from the library using Python scripts,
So it writes the code describing the circuit.
effectively assembling the circuit digitally. This also involves sophisticated computational mapping and transistor sizing using established techniques for these standard cells, ensuring each component is correctly dimensioned for optimal performance. The output is a complete, machine-readable netlist for the analog chip.
A complete, highly detailed blueprint for the circuit. And then the final, absolutely critical stage is about making sure this entire automated process actually yields a circuit that works exactly as intended.
Exactly. Verification is key. Stage 5. Functional simulation and validation. This is where the rubber meets the road.
Testing the design.
The generated netlists undergo rigorous validation using industry-standard SPICE tools. SPICE, or Simulation Program with Integrated Circuit Emphasis, is the gold standard for analog circuit simulation.
The industry workhorse.
We leverage Cadence Virtuoso for visual inspection, allowing designers to physically see the schematic and Cadence Spectre for functional validation to run detailed simulations and ensure the circuit behaves precisely as expected, meeting all performance criteria.
Making sure the analog output matches the math.
And importantly, once validated, the layout can be generated by using this schematic on Cadence Layout GXL through the automatic place and route features of the standard analog cells,
So it connects to the physical chip design tools.
directly linking this automated high-level design flow all the way to physical chip implementation and manufacturing. It seamlessly integrates into existing industry workflows.
So what does this all mean for someone wanting to build a complex analog system? We've got this incredible multi-stage process taking a high-level idea and turning it into an actual verifiable circuit.
It means a massive speed up and reduction in specialized effort.
Can you walk us through a real-world example, say building a Bayesian network with KALAM, to make these stages truly concrete and illustrate that flow?
Absolutely. This raises an important question. How does that abstract factor graph actually manifest physically through all these stages?
Right, how does the graph become silicon?
The elegance lies in the modularity of MP circuits and KALAM's ability to systematically leverage them. When we generate the computational graph, we're essentially breaking down a complex problem into smaller, manageable mathematical operations.
Stage 2.
Crucially, each of these operations has a pre-designed, optimized analog equivalent in our library of MP standard cells.
Stage 3 picks those.
This allows us to rapidly compose incredibly complex systems, much like building with advanced Lego bricks, but with all the interconnections and optimizations handled automatically.
Okay, so let's take that Bayesian network example.
Let's consider the compelling example provided in our sources. A simple prey-catching scenario. Imagine a Bayesian network trying to infer if a prey will be caught based on factors like whether a predator is active or visible.
A classic probabilistic inference problem.
Exactly. KALAM gives by performing a factorization of the probabilities to convert this problem into a factor graph that's stage 1.
Turning the problem into the graph language.
For instance, you might have factor nodes representing conditional probabilities like F1 equals P, catch fangs out, or F2 equals B's, base from P, fing, predator active, predator visible.
Right, so taking real-world probabilistic observations and translating them into that universal factor graph language.
Exactly. For very simple networks, you might even visually identify if a factor node, say F3 equals P mouse appears, predator visible, is unrelated to node catch and thus can be eliminated.
You could maybe see that on paper for a tiny example.
This kind of manual optimization is intuitive for small cases.
But for larger, more complex networks, which is the whole point of KALAM, you wouldn't be able to do that manually. The sheer number of variables and dependencies would be overwhelming.
Precisely. For large networks, this is not feasible to manually identify and eliminate unrelated nodes or redundancies. This necessitates the automated computational graph generation of stage 2,
where the tool does the heavy lifting on optimization.
Here, those abstract factor nodes are unrolled to represent computations in the computational graph, outlining the exact sequence of mathematical operations. This optimized computational graph then forms the basis for the analog map in stage 3,
picking the MP circuits,
where specific MP analog standard cells are selected and configured for each required operation, whether it's multiplication, addition, or a nonlinear activation. Finally, in stage 4, KALAM generates the precise SPICE netlist,
the circuit blueprint. And for validation in stage 5, how do we know this generated analog circuit actually reflects the probabilities it's supposed to compute? How do we verify its accuracy?
Good question. For the SPICE validation in stage 5, the input magnitudes are meticulously mapped as a multiple of 1 in a current. This is a critical tunable parameter that allows fine-grained control over the analog computation.
So the input current represents the input probability or value.
Essentially, yes. In our prey-catching example, if we were trying to infer p-catch1 predator divisible 1, the probability of a successful catch given the predator is visible. The output current of the soft OR gate, which combines the relevant probabilities, was found to be 0.524A.
And what should it have been mathematically?
Crucially, this measured current corresponds very closely to the expected mathematical output of 0.555.
Okay, 0.524 versus 0.555. That's pretty close.
Very close. The slight difference, as we'll discuss shortly, is a known artifact inherent in continuous time analog simulation. But the close correlation is a powerful validation of KALAM's accuracy.
That's a strong correlation, clearly demonstrating that the analog circuit is correctly performing the probabilistic inference. And our sources also provide a visual representation, a layout for the KALAM-generated netlist. What does that look like on an actual chip?
Yes. If you look at the visual provided in our sources, you can see a clear layout for the KALAM-generated netlist for this Bayesian network.
The physical chip layout.
It shows the physical arrangement of the automatically placed and routed components. Specifically, 8 soft AND gates, each mapped to a multiplier, and 2 adders, which are cleverly implemented by simply adding currents based on Kirchhoff's current conservation law.
Using basic physics for addition. Neat.
You can even see a zoomed inset of a single soft AND gate, giving you a concrete visual of how these highly optimized automated designs translate directly into physical structures, down to the transistor level on a silicon chip.
Wow.
It's the ultimate proof that the abstract factor graph can indeed become a tangible, functional piece of hardware through KALAM's automated flow.
So the proof is truly in the pudding. KALAM isn't just a fascinating theoretical concept. It's actually building these incredibly complex analog systems with remarkable accuracy and unprecedented speed.
It seems to be delivering, based on these examples.
Can you walk us through some of the real-world performance metrics and validation results, demonstrating its practical efficacy across different domains?
Absolutely. This raises an important question. Does it work in practice? And the data overwhelmingly confirms its efficacy.
Let's hear it.
The remarkable alignment between the netlist simulation results from KALAM's automated flow and the ground truth software implementations. Across a diverse set of applications like Bayesian networks, LDPC decoders, and artificial neural networks, profoundly validates this automated approach.
Consistency across different types of problems.
And the sheer speed generating complex circuit netlists in milliseconds is truly transformative for rapid prototyping and accelerating development cycles. Let's start with the results for Bayesian networks.
Okay, the probabilistic models. Tell us more about those Bayesian network results. What kind of data was used and how did the accuracy hold up?
KALAM was rigorously tested on 5 different Bayesian networks derived from datasets found in Kaggle, which are real-world, publicly available data sources.
So, real data, not just toy problems.
Exactly. This included a diverse range of models, airplane, Titanic, pistachio, thyroid, and drought datasets, each representing different complexities and numbers of variable nodes. The results were exceptionally compelling.
How close was the accuracy?
We observed an almost identical correlation between the software accuracy, our ground truth, and the netlist accuracy obtained from KALAM's generated analog circuits across all models.
Really? Almost identical.
For instance, the airplane model showed 82.38% software accuracy versus 82.27% netlist accuracy, a difference of just 0.11%.
Wow.
The thyroid model achieved 95.3% for both. This negligible drop in accuracy, often less than 0.5%, is crucial, indicating that the analog implementation faithfully executes the probabilistic inference.
That's incredibly important for real-world applications maintaining accuracy when moving from theoretical software to physical hardware. What about the speed of design for these complex networks?
You mean how long it took KALAM to actually generate the circuits?
Yeah, how long did KALAM take to generate these intricate circuit netlists?
The synthesis runtimes was astonishingly fast, consistently recorded as less than 7 meters for generating these complex Bayesian network netlists.
Milliseconds. Less than 7 milliseconds.
Yep. To put that in perspective, this is virtually instantaneous. For an analog designer who might spend hours or days on even simpler circuit blocks, generating a full system in milliseconds is truly revolutionary.
Mind-blowing speed up.
For validation, the ground truth software accuracy was established using the pgpy Python library, a standard tool for probabilistic graphical models, and netlist analysis was performed with Cade Inspector using industry-standard simulation tools. This shows the results are robust and verifiable.
So fast, accurate, and validated for probabilistic inference. What about something foundational to modern communication, like robust error correction with LDPC decoders? How did KALAM perform there?
Good question. For LDPC decoders, KALAM demonstrated its capabilities by implementing a 32-bit regular LDPC code with specific structural parameters, a 4-degree factor node and a 3-degree variable node.
Okay, a specific type of code.
And to rigorously demonstrate its scalability, this 32-bit code was then intelligently expanded to 64-bit and 96-bit code lengths using the protograph technique.
Scaling up the complexity.
The protograph technique is an advanced method for constructing large, high-performing LDPC codes from smaller base graphs, allowing for systematic scaling while maintaining good error correction properties.
Got it. So how did it perform on correcting errors?
The bit error rate, BER, and frame error rate, FER, plots presented in our sources show an incredibly strong correlation with software results across varying signal-to-noise ratios.
So the analog decoder worked just as well as the software version?
Pretty much identically. Yeah. This unequivocally affirms KALAM's reliability for these mission-critical communication tasks, meaning the analog decoder performs just as effectively as its digital software counterpart in correcting errors.
That's fantastic. Error correction is a make-or-break aspect of digital communication. And the runtime for synthesizing these increasingly complex decoders, did the speed hold up?
Even with the increased complexity of longer codes, the synthesis runtimes remained incredibly efficient. 32 meters for the 32-bit code, 39 meters for the 64-bit, and 51 meters for the 96-bit code length.
Still milliseconds. Slightly longer, but incredibly fast.
Yeah, absolutely. This further underscores KALAM's capacity for rapid, scalable design. It's also worth noting an important flexibility. KALAM integrates both MP and non-MP designs for these decoders.
Ah, so it can mix and match circuit types.
Exactly. This showcases its broader applicability, demonstrating that while MP is its core, it's not exclusively limited to it and can leverage other optimized analog blocks.
That flexibility is a powerful testament to the framework's design. Finally, how did KALAM fare with artificial neural networks, the ubiquitous backbone of modern AI, especially for edge applications?
Right, the AI part. For artificial neural networks, KALAM was used to design a network with a practical architecture. 4 input nodes, 8 hidden nodes, and 3 output nodes.
A small but realistic network.
Utilizing the critical M operation and ReLU activation function, using the well-known IRIS dataset, a common benchmark for classification tasks.
Standard AI benchmark.
The software testing accuracy was found to be 90.5%. Remarkably, the netlist accuracy was also found to be 90%.
Wow, again, almost identical performance.
Again, a very close match between the software's performance and KALAM's analog hardware implementation, highlighting its capability for robust, efficient AI at the edge.
Those results across such diverse, demanding applications, probabilistic inference, robust communication, and AI are incredibly consistent and compelling.
Yeah, the numbers look really good.
What's the overall takeaway regarding KALAM's performance and its real-world implications?
The summary is unequivocal. KALAM is a game changer for analog design. The runtime to generate the netlists of all the designs implemented by KALAM is observed to be ones pans for an Intel i7 processor.
Less than a second for any of these complex systems.
Exactly. To put that in context, for an analog designer who spent weeks wrestling with spicy E-simulations and manual transistor sizing, generating a functional netlist in milliseconds feels like witchcraft.
Or just, good automation.
This is orders of magnitude faster, truly transformative compared to manual design, which could take weeks or months for even simpler systems, let alone these complex networks.
And the accuracy, we saw tiny differences.
Regarding accuracy, our sources acknowledge a negligible drop in the accuracy for Bayesian networks and a similar close correlation for others. The slight differences observed between software and SPICE simulation results are a known artifact of continuous time analog simulations.
Right. Analog isn't perfectly discrete like digital math.
As reported in prior research,
Yes.
reflecting the inherent characteristics of analog systems versus discrete digital models. However, the similarity of the implemented results with the baseline design reported in 2 is a testament to the tool's efficacy in both implementing and integrating MP and non-MP modules.
So the results match previous work, which adds confidence.
Exactly. KALAM has proven its ability to deliver high-performance, accurate analog circuits with unprecedented design speed.
So it's fast, incredibly accurate, and robust across fundamentally different computational paradigms, truly validating KALAM's effectiveness as an automated design platform.
That seems to be the conclusion from the data presented.
This all sounds incredibly impactful. KALAM isn't just a neat trick or an incremental improvement. It seems to be addressing a truly crucial, long-standing gap in the world of chip design.
A major pain point for analog designers.
Our sources point out that while significant efforts have been dedicated to optimizing fundamental analog circuits, think basic building blocks like operational amplifiers or filters automation for large scalable analog circuits is less explored.
Right, focus has been on the small pieces, not the big picture assembly.
Where does KALAM fit into this broader landscape, and why is its approach so unique compared to previous attempts at analog automation?
If we connect this to the bigger picture, KALAM isn't merely a tool. It represents a genuine paradigm shift.
A shift in thinking.
It takes the inherent advantages of analog computing, like its energy efficiency, its speed for certain tasks, and its native ability to handle continuous signals, and systematically removes the biggest historical barrier to its widespread adoption: the complex, agonizingly manual design process.
Tackling that core bottleneck head-on.
When we examine the existing landscape of analog design automation, most prior efforts, as our sources indicate, have focused on low-level tasks like optimizing transistor sizing or perfecting the topology of individual components.
Fine-tuning the tiny details.
KALAM, however, operates at a much higher level of abstraction. It's tackling high-level synthesis for complex, scalable analog systems, an area where previous solutions were largely non-existent.
Moving up the design hierarchy.
This fundamentally democratizes analog design, enabling innovation to occur at a pace previously unimaginable.
So it's elevating the level of abstraction for analog design, bringing it much closer to the automated high-level synthesis that digital designers have enjoyed for decades.
That's the goal.
Allowing them to focus on functionality rather than individual transistor minutiae. And you mentioned earlier that margin propagation is absolutely key to enabling this level of automation.
Yes, MP is crucial.
Why exactly are MP-based designs so uniquely suitable for automation compared to other analog approaches?
It comes back to those inherent qualities we unpacked earlier. Their ability to be pre-characterized, modular, and robust like digital designs.
Predictable, reusable, tough.
These are the fundamental enablers for KALAM's automation. Imagine trying to automate the construction of a building where every single brick was slightly different, unpredictable in strength, and reacted uniquely to every environmental factor.
Chaos. Impossible to automate.
It would be impossible. Traditional analog components often behave that way, requiring endless manual tuning. But MP circuits provide that reliable, repeatable, and well-behaved foundation.
The standard building blocks.
Because they're modular, designers can logically decompose complex problems. Because they're robust, they aren't thrown off by minor variations. And because they're pre-characterized, KALAM can treat them as standard cells, allowing it to programmatically compose them into complex systems.
Like snapping Legos together reliably.
This consistency is not just an advantage. It's the very backbone upon which KALAM's automated synthesis stands.
That makes perfect sense. Predictable, modular building blocks are absolutely essential for any successful automated system. And KALAM isn't just limited to MP-based designs, is it?
No, that's an important point.
Our sources hint at an even broader, more ambitious vision for the tool's future.
That's right, and it speaks to the foresight of the developers. The framework further supports the integration of non-MP modules, which is compelling evidence that KALAM can be used for non-MP designs as well.
So it's not an MP-only club.
Not exclusively. This extends its utility significantly, allowing it to incorporate other, perhaps existing or future, optimized analog blocks beyond its core MP foundation.
Making it more versatile.
And the authors themselves are actively looking towards future versions of KALAM. Their plans include exploring the synthesis of other graphical models beyond those already demonstrated.
More than just factor graphs eventually.
Perhaps, or different types of factor graph applications. And also various machine learning architectures for both MP and non-MP analog computing.
Tackling more AI models.
This suggests a powerful ambition to make high-level analog synthesis a reality for a much wider array of applications and circuit types, solidifying its role as a universal platform.
This raises an important question. What does this fundamental shift, this democratization of analog design, truly mean for the devices and technologies you, our listener, use every single day?
Yeah, what's the real-world impact?
Could this be the key to unlocking truly pervasive, ultra-low-power artificial intelligence, or vastly more efficient sensors and communication systems that we can't even fully imagine yet?
Absolutely. Think about the potential ripple effects. Tools like KALAM will profoundly accelerate the development of the next generation of energy-efficient AI, edge computing, and smart devices.
Faster innovation cycles.
Today, building a custom analog AI chip for a specific application is a monumental undertaking, often requiring years of highly specialized expertise and significant financial investment.
Only feasible for big players, usually.
By effectively democratizing analog design, KALAM lowers that barrier to entry. This means more engineers, more startups, more researchers can rapidly prototype and develop cutting-edge analog solutions.
Opening the door for more people.
This could translate directly into faster innovation cycles, dramatically lower development costs, and ultimately a new generation of more sophisticated, vastly more power-efficient devices.
Like what kinds of devices?
Imagine AI that runs directly on tiny self-powered sensors, making your smart home truly intelligent and responsive, or wearables that offer continuous health monitoring without constant recharging.
AI everywhere, without killing batteries.
It's about enabling pervasive computing by making the underlying hardware design accessible and efficient.
So it's not just about slightly better chips, it's about enabling a whole new class of computing by removing the biggest, most stubborn bottleneck in analog design that has held it back for decades.
That seems to be the potential, yes.
It's truly enabling a future where power-hungry digital systems might be intelligently offloaded to their energy-efficient analog cousins.
A hybrid approach, leveraging the best of both worlds.
And that brings us to the end of another deep dive. Today, we've journeyed into the heart of KALAM, a groundbreaking toolkit for automating high-level synthesis of analog computing systems.
Quite a journey into the world of automated analog design.
We've seen how this innovative framework provides automated, digital-like synthesis for the next generation of energy-efficient analog computing systems, leveraging the foundational power of vector graphs and the robust modular margin propagation framework.
Connecting the high-level math to low-level robust circuits.
We've explored how KALAM takes high-level problem descriptions and systematically translates them into functional physical circuit netlists through its ingenious 5-stage automated flow.
From idea to verifiable netlist, remarkably fast.
KIT's success has been rigorously validated across incredibly diverse applications, from complex Bayesian networks performing probabilistic inference to robust LDPC decoders ensuring reliable communication, and even artificial neural networks powering edge AI, consistently demonstrating remarkable accuracy and truly transformative design speed.
KALAM really highlights how targeted intelligent automation can unleash the immense potential of computing paradigms that were previously constrained by their sheer design complexity.
Breaking down those old barriers.
It's more than a tool. It's a critical bridge between the abstract world of algorithms and the physical reality of highly energy-efficient hardware, enabling us to do more with less.
It truly is. As our digital world demands more and more from hardware, facing ever-increasing energy consumption and performance challenges,
Which it constantly is.
could this strategic return to intelligent analog design, supercharged and made accessible by automation like KALAM, be the definitive path to truly sustainable and powerful computing at every single scale?
A fundamental shift back towards analog, enabled by digital-like tools.
It's a profound thought to ponder as you look at your next smart device or consider the future landscape of artificial intelligence. This shift isn't just about faster development. It could fundamentally impact everything from the battery life of your smartphones to the ubiquity and efficiency of AI, making it more pervasive and powerful than ever before.
The potential is definitely there.
Thanks for joining us on the Deep Dive. We'll be back next time with another exploration into the research that truly matters.